Our goal for this lesson is to graph all of these basic functions and without having to make a table every time. And my goal is that you'd be able to graph each of these functions in 5 seconds or less just by seeing the parent function. This first one, a parent function that is a constant function, we can imagine f of x equals 1 just being the standard parent function. Now if I wanted to graph f of x equals 1, remember that's the same thing as y value equals 1, and we have a bunch of points that have a y value equal to 1, and they all lie along this horizontal line. So that's the parent of all horizontal lines, the function f of x equals 1. This next one, f of x equals x. Again, that's just the same thing as y equals x. We can think of a lot of points where the y equals the x, like 1, 1, 2, 2, 3, 3. The y value equals the x value. Some people even think about that as mx plus b, where the slope is 1 and the y-intercept is 0. And that's the parent of all slanted lines. So we could do transformations to that and get any slanted line we wanted. The absolute value function, I'm going to make a table this time, but remember our goal is to do these graphs without having to make a table. When we take the absolute value of a negative number, it just becomes opposite of what it was. The absolute value of positive numbers are the numbers themselves. And so maybe you remember this one, 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. And so just now that I've reminded you what the absolute value function looks like, I'm sure you could graph that really quickly when you see y equals absolute value of x. The square root function maybe not quite as familiar. So this time only, let's make a table. And I'm going to choose numbers that have nice square roots, because I know I'm going to be plugging those in to this. So square root of 0 is 0, square root of 1 is 1. You'll notice I didn't use any negative x values because I don't want to be taking negative or square roots of negative numbers. 0, 0, 1, 1, 4, 2, 9, 3 would be on there, but it's off my paper this time. I would like you to be able to graph those points in 5 seconds or less, but maybe without having to make that table every time. But knowing that the square root of 1 is 1 and the square root of 4 is 2, I think we can handle that. This one you're so familiar with, y equals x squared. You might not even have to look at this. Negative 2 squared is positive 4. And so 0, 0, 1, 1, 2, 4. So I do care about the accuracy, but I want it to be a quick sketch of the graph, even so. But you should know where those big points are. X cubed. I usually just like to think of 2, 1. I can cube a negative 2. Negative 2 times negative 2 times negative 2. Negative 1 cubed, 0 times 0 times 0, 1 times 1 times 1, 2 times 2 times 2. So 0, 0, 1, 1. Okay, 2, 8 is going to be way up there. So that just tells me that when I graph this 2, 8 way up there, this just grows really fast. Negative 1, same thing down here. It's going to drop down really fast, down to that negative 8. And that's our parent cubic function. These last two are maybe a little more unfamiliar. The reciprocal function. So we could do a negative 2 and a negative 1. The reciprocal of negative 2 is negative 1/2. Or you could think of that as actually plugging that in. 1 over negative 2 is negative 1/2. 1 over negative 1 is still negative 1. Since it's called the reciprocal function, let's have some fun. 1 divided by 1/2. 1 divided by 1/2 is 2. I guess I should have made that one negative. But you get the idea. What's 1 divided by 0? Undefined. And then those halfsies are, the positive ones work the same way. So the reciprocal of 1/2 is 2. The reciprocal of 1 is 1, the reciprocal of 2 is 1/2. Let's graph those. If you're not sure what's happening, that undefined bit, oh, I totally missed. That undefined piece is a vertical asymptote. So that's the parent reciprocal function. Again, we can do transformations and make that into a lot of sort of different graphs, just going off of that one basic graph. The greatest integer function, some people call it the rounding down function, some people call it the floor function, I suppose because you're rounding down. Sometimes I like to think of it as sort of an age type of function. I'll show you what I mean. So the day you turn 1 year old, you call yourself a 1-year-old. But even as you grow throughout the year, if you're 1.2 years old, we still call you a 1-year-old. Even a 1.7-year-old is still only 1. A 1.9-year-old is so close to their birthday, but they're still only 1. It's a rounding down function. Same thing with 2. The day you turn 2, you're 2, and you stay 2 until you hit that next birthday. So what would that look like on a graph? We'd have a point at 1, 1. 1.21, 1.71, 1.91, and basically you're going to have like this little flat line until you get up to x equals 2, and then you're up at 2, and then you stay up at 2 for all of those x values. And so the graph is a lot of times called a step function. We can fill that in. But again, it's just sort of a rounding down function. One other thing you should think about is right at the edges of those steps. I know I definitely have a point at 1, 1. I definitely have a point at 2, 2. But then in order to get the vertical line test working, we have to think, would a 2-year-old ever call himself a 1-year-old? Not a chance. And so that's why we'd have an open circle on each of the right sides of this graph. That is called the greatest integer function. It's kind of a nice one when we get to transformations. So again, the goal of this lesson is that you could graph each of these functions in 5 seconds or less without having to make a table. You could plot those points on there, knowing just where those intersections are.